So, welcome everyone for the first lecture of CEE 08383 Analysis and Design of Steel Frames. My name is Dr. Islam Mantawi, an assistant professor at Civil and Environmental Engineering at Rowan University. And in this semester, I will be teaching this section of Analysis and Design of Steel Frames on Monday and two lectures on Wednesdays. So in this specific lecture, I'll be covering in some YouTube recording all the slides in all the lectures throughout the class. It should be noted that this is not a substitution of attendance in class, as attendance in class will be heavily weighted in your final grades. It only serves as resource for you for whatever you missed throughout the class. Given that you cannot absorb 100% of materials, this lecture serves to provide the basic informations needed for you to remember what was discussed in the class. Please note that could be much more information based on the discussion during the class with the students as a Q&A sessions, and also some clarification beyond what is recorded in this session. So as we mentioned, this is CEE 08383 Analysis and Design of Steel Frames, Spring 2024. My name is Islam Mantawi. My office is located at Rowan Hall, room 230. My email address is shown. And also, just as a reminder, we meet in person on Mondays at Engineering Hall, room 320 from 11 a.m. to 12:15 p.m. Also, we meet for two lectures on Wednesday at Engineering Hall 320. The first session or lecture will be from 8 a.m. to 9:15 a.m. with another 15-minute break. We will have another session from 9:30 to 10:45. My office hour this semester is on Mondays from 2 p.m. to 5 p.m. in my office at Rowan Hall 230. And also you can reach out for appointment through an email, and we can set up either virtual or in-person office hours. And also I'm showing the link for my remote meetings using my WebEx page or WebEx link. For communication for this class, please use my email address mantawi@rowan.edu. Please provide in your subject line of the email the following information. You start with CEE 08383, and after that follow up with your subject. For example, if you have question related to homework number 1, your subject should be CEE 08383 homework number 1. Please note, in this class, we will have to have a required design manual, steel construction manual, latest edition of 16. We will not be using this year 15 edition. And I believe that I communicated with you a week before starting of the class to purchase your manual through a discount. And since this manual, edition 16, is really recently just published, you will not have any other resources that could be competitive to purchase the code aside from the link that I provided you. We also recommend a textbook, which first will be my slides, which can serve as online reading materials. And also, if you need to have an access to structural design, steel design book by Jack McMorrow and Stephen Kiselnik, edition 6. You can reach out to me to provide you information how to access the book as online version this semester. This course objective is shown on this slide. The course is an introductory course, the first course for design for you in a structure area that focus on fundamental and concept of steel design for civil engineering students. The objective of this course are instilled in each student an understanding of the theory and logic behind the design equation used for select steel section. We begin with an introduction to the field, and students gain more information about the properties of material, understanding of manufacturing processes, and structural characteristics. The student should be able to understand different type of structures, load and load combination, and the basic analysis design of tension, compression, and flexural members. The student should have solid understanding of buckling modes, such as local buckling, torsional and torsion flexure buckling. And it is potential for structural failure. Its potential for structural failure in overlooked in design. The course introduced key design philosophy, emphasis on limit state design, allowable stress design, and load and resistance factor design alongside the steel connection, covering both bolted and welded connection. They should be appreciated the importance of their work presentation and structural engineering ethic responsibility. So for the grading of this class, you will have 25% on final exam, 25% in quiz exam, which is either quizzes in the class and the midterm plus the midterm. Design project 20%, homework 20%, small project on iconic steel structure 5%, and attendance 5%. Your grades based on the numerical scores shown. Please note that you cannot get less than C minus in this class to pass. Lower grade for A minus or A minus is 90%, for B minus is 80%, and C minus is 70%. So for the course content, you will have a very modular course where some subjects are not intersected. So we have it in here in different slide as blocks. So for example, here we will spend Wednesday of January 17th, lecture 1, lecture 2. Lecture 1 will be on introduction to the class and very quick review on structure analysis. So we'll go through how to get the reactions on beams, how to draw, how to remember V and M shear and moment signs, how to draw shear and moment diagrams, etc. And this actually could finish fairly earlier in the lecture. So in this first lecture, we will start the first part of introduction, which is specification, load combination, and method of design, including structure stability, which also will be covered in the second lecture on Wednesday, January 17th. Next week, Monday, January 22nd, we will continue and we'll also focus on how to calculate torapotary areas on beams, girders, columns. And we will also start introduction to what is a steel design should be. This will also be covered in the first lecture of January 24, 2024, where we will cover structural steel design, advantage and disadvantage of steel, and steel sections and material properties. So we will cover the first topic. First design topic is design and analysis of tension members in almost hopefully 5 lectures. The first will start on Wednesday, January 24, and with a projected end of this topic on Monday, February 5th. The second design topic will be topic number 3, which design of compression member or member subjected to axial loading in compression. We predict that we will need 4 lectures to cover this topic. This will start on Wednesday, February 7th, and on Wednesday, February 14th. There will be a design of flexure member or member subject to moments or flexure stresses. This will be projected to be covered in 7 lectures, started from Wednesday, second lecture of February 14, ends at the end of the month, Wednesday, February 28. On March 4th, we will have the midterm exam review, which will cover all topics covered before this session on March 4th. Your midterm exam will be the first lecture on March 6th. Wednesday, March 6th will also finish the last topic of lecture members, which will not be included in the exam. Remember, the week of March 17 to 15 is spring break, and right after spring break on Monday, March 18, we'll have a project day. Right after the midterm, we will have to start topic number 5, bolt connections, for both analysis and design. We will also it will be expected that we'll finish that in 5 lectures, starting on Wednesday, March 20th, ending on Wednesday, March 27th. We will continue on April 1st to Wednesday, April 3rd, topic number 6, which is welded connections, analysis and design. We will have a project day on Monday, April 8th. We will have Wednesday, April 10th, as a mock-up to cover any missing topic or any underestimation of each topic lectures. On Monday 15 through April 22nd, we will talk about how to design beam columns or sections subject to both axial and bending moments. On Wednesday 24th, the entire day will be a review and project delivery and final exam on the week of April 29th. Now we will start our review on structural analysis. So for this problem, example number 1, we have a simply supported beam AB. It has 12 feet span or length. It has 600 pounds, 4 feet away from point A. And it's required for you to solve for reactions. To solve this one, you remember from structural analysis, you have to have your sigma force at X equals 0, sigma force in Y direction also 0, and sigma moment around any point should be equal 0. We will take advantage of this equation. We will take moment around point A. This will give you the moment around this point. RA will be cancelled because the arm is 0. We will assume that this is gonna be your positive moment counterwise. As you can see here, the reaction RB is turning around point A at counterclockwise. So here RB times 12 feet positive minus 600 is gonna rotate clockwise, so it's gonna be negative. So minus 600 pounds times 4 feet will be equal to 0. To solve this equation, your RB will be equal 200 pounds. Similarly, if you take the moment around B, which is going to be this point now, your RA will be negative RA because RA around point B will turn clockwise times 12 plus, since 600 pound is turning around B as counterclockwise, will be 600 pound times 8. That will be equal to 0. From this, you can get RA as 400 pounds. If you want to check this equation, Fy, sigma Fy equal, RA is 400 pounds, RB is 200 pounds, so 400 pounds negative, positive going up, plus 200 pounds minus 600 pounds, which is downward. This is all the load you have, so this is going to end up 0. So this is going to be how you solve for reactions. To solve for shear diagram, given that the RA is 400 pounds and RB is 200 pounds, you need to draw the the shear diagram. So the shear diagram here, given that you have 12-inch span that is divided at the load for the first segment to be 4 feet, and the second segment is 8 feet. You always gonna start with the upward to be the positive. So at the support RA, you have 400, so you have to draw 400. The shear at any point is the forces from the left or the right. Here, what you can see, that any point before 600 pounds, we can call it point C, will always have shear of 400 that will yield for you a constant shear. Once you pass the right side of 600 pounds, you have to draw a drop of 600, which can give you 200. And this also will be constant until you meet the reaction 200 and you close at 0. So this is going to be your shear diagram. To draw your bending moment diagram, since we already draw the shear moment diagram as 400, that constant for 4 feet, drop to 200 negative for 8 feet. This is negative, this is positive, and the distances are 4 feet and 8 feet. So you can directly get the moment by, let's say you need the moment at this point, which we're going to call it C, by the area of the shear diagram. So what you can do now, what you can do is the moment at point C here will be the area of the shear diagram. In this case will be 400 plus times 4 feet, which is going to end up 1600 pound foot. If you calculate it from the left side, it will be 200 times 8, which is the same as 16 pound per foot. And since it is a uniform concentrated load, so this line is flat, this is going to be a sloped line. So in the moment is the integration of this horizontal line. This is example number 2, where we have almost the same beam, 12 feet span, between point A and B, simply supported, hinge on A, roller on B, but we have a uniform load of 75 pounds per foot, only located at the first 8 feet from point A. And it's required that you solve for the reactions in this slide. So if you want to calculate such reaction, what's required is that you have 75 pounds per foot, that is 8 feet from point A and ends 4 feet away from point B. In this case, you can have the resultant of 75 pound per foot, which is going to be the resultant of the load will be 75 times 8, which is going to give you 600 kips. This can be used to get only the reactions. So this is your resultant at the middle because it's a uniform load, and you can get 600 kip. Luckily, this is going to be very similar to what we did in example 1, when we have 4 here and 8 there, and the reaction, if you're going to go to this slide, back to this slide, RA was 400 pound and RB was 200 pound. Since now we know the reactions, at B was 200, at A is 400 pounds, and our load now is uniform load. From this step, you should not be using the resultant, you should be using the actual load, which is 75 pounds per foot. So in order to draw the shear diagram, you're going to do the same. Every time you have a load going up, you will go up 400. Then, since you have here 75 pounds per foot and a distance of 8, that means every foot you have to drop 75 pounds. So that will yield you, if you do that, you're going to have to drop for first feet 75 pounds, going to be 325. And if you can keep doing that, you will reach to 200. At this point, there is no loads until you meet the support and go back up 200. So this will be the positive shear, and this will be negative shear, and this is going to be your shear diagram. To calculate the bending moment diagram, let's draw again the shear diagram. The shear diagram was 400 from the left on a positive sign, 200 in a negative sign. We will have a flat line here, and you'll have inclined line here. Since this is 400 and this is 200 and this distance is 8 feet, you can have by interpolation the relation between this distance and this distance will be similar to this distance to this distance. And since this distance is 8 minus x and this is x, you can actually solve for x, saying x over 400 should be equal 200, 8 minus x divided by 200. That's going to give you, if you cancel, you will have 2 here. So you'll have half x equal to 8. Sorry for this. 8 minus x. If you solve for x, x will be 8. Very hard time to draw 8. Divided by 1.5, which is going to give you a 5.67. And in this, if you this distance will be 5.33, and this be 2.67, and this is 4 feet. To draw the bending moment diagram now, this is going to be the left side, so it's going to be the area of 400 times half, because it's rectangular, times the distance 5.33. So 5.33 times 400 times half will give me a moment of, at this point, moment of 10.67. If you draw also the moment, the areas around from this side to get the moment at this point, you have to subtract this area, which is half, times this area is half, times 200 times 2.67. That give you 0.5 times 200 times 2.67. It give you this area should be 267 in negative. This area is half times 400 times 5.33. So, which what we did here, 1067. And here will be 1067 minus 267, which is 800. To draw here, this is a flat line, so this should be a sloped line, as this is the integration of a flat line. And since this is an inclined line, this should be a parabolic curve. So this is going to be your bending moment diagram. I'm drawing the bending moment diagram on this side. You also can flip it and it should be the same. Example number 3, we have a simple beam of 12 feet span. We have a concentrated moment at 4 feet away from point A of a magnitude of 1200 pounds per foot. In counterclockwise direction means positive. In order to get a reaction here, what you're gonna do, you take a moment around A to get RB. So the moment is 1200 positive because it turned around A as anticlockwise. However, in this direction, we assumed RB vertical, so it has also to rotate around A as clockwise. So we have plus RB times 12 equals 0. That means RB from this equation has to be negative 100 pounds. In order to get RA, you can take the force around Y equals 0. You know RA is assumed to be up, so it's positive. RB was up, but the value is negative. So negative 100 is equal to 0. That gives you RA equal to 100 pounds. So your assumption for a direction of RA is correct, but for RB it should be the opposite direction. So let's draw it again with our reactions to get the shear diagram. So we have the load as moment of 1200 pounds per foot. We got RA as 100 going upward. We have RB is 100 but it's downward. If you want to draw the shear diagram, for the shear diagram, it's very simple. You go from A up, there is no loads, so you keep going constantly and you drop down after you meet 100. So this value will be 100 and your shear heel is positive, and this is your shear diagram. To get the moment, it's actually the same way. If at this point we call it C, you will need to take the area of this shape, which is going to be 100 times 4 feet, because this distance is 4 feet. And you can draw it in either way. If you want to draw it the 400 at this direction, because the total is 400. You can also calculate from the other side the moment, and in this case, the moment will be clockwise. Clockwise is negative. So this will be 800, which is the area of this flat shape, flat line or rectangle, which is 100 times 8. And you transition between the two in 1200 drop, which is the external moment. This ends the first subtopic of topic number 1, topic 1-1. I look forward to the next topic.